Hello, AP Calculus students. We're kind of about halfway through our class here on Tuesday, the 4th of January, 1422. And we're going to go ahead and jump right into section 4.2.1. And I suspect we'll probably get through 440. We'll probably look at 441, and that will probably be enough for today, especially because I want to take our time with 441, because there's a lot of calculations we have to do. However, I'm hoping that at the end of 441, you'll start to see the main method that you'll be using for evaluating integrals outside of just using geometry for things. So we're going to start connecting together the idea of a derivative and an integral, because there's kind of three main ideas in AP Calc AB. Number one, derivatives. Yeah, I know. Do you guys see my cool TikTok I made yesterday that's going viral about? Yeah. Yes, it's true. Derivatives, which are used for measuring the slope of a function at an instantaneous point. And you can also do second derivatives, which tell you about concavity and all that stuff. Then you have integrals, which are, we've been using them to measure the area under a curve between 2 points. But the next step, what we're going to start looking at in this section in particular, 4.2, is the third and probably the most important part of this, is that derivatives and integrals are opposites of each other. And I can tell you that today, and you can probably say, cool, I agree with you, Mr. Ford, and be just happy. But we're going to spend some time proving this idea and analyzing why it works. And we've seen this from the beginning, from like the very first lesson, which is referenced in the first homework problem in 4.2.1. From the first day when I showed you a graph of a distance that a truck had traveled, and then the velocity of a truck. And we were able to use the area under the curve of the velocity graph to figure out how far the truck had traveled. We've been doing this the whole time. It's just been kind of like hanging out in the background. The slope of a function ends up being its derivative, or you can take the slope of distance and get velocity, or you can look at the area under velocity and get distance. Those are the same basic idea. So we're going to be starting tying that together. But let's just explore a couple problems together, and maybe you'll see what I'm hoping that you'll see about this. Let's start with 440. Determining slope functions is powerful because they offer the ability to express the rate of change of a function for all values x in the domain. However, what about the area under a function? How can we also write an area function a that will calculate the area for all values t in the domain? The main goal of this problem is to figure out question D, a of x. And I really want to zoom in on D for a minute. Before we explore it, I really want you to look at that function and ponder for a moment what's going on in that function. Where is the x in that function? It's not in the integral. It's actually up here. It's the right endpoint of our integral. So what's happening here is that we're actually anchoring the left endpoint in place. And now the variable is, kind of imagine that drawing over there on the board. Imagine that A was locked into place, but B was allowed to slide to the right. What would the area under the curve be if you let that X change to the right? If you lock a 0 in place, but slide X to the right. To explore that, we're going to find a couple of easy area calculations, because you'll notice that if you look at A, B, and C, we've got 0, 1, and 2. Hopefully, by doing those three problems, we'll be able to see a pattern that we could use to write like a general function that would work. And this is a pretty easy one because that graph is just a constant graph. In fact, in this case, we're going to call it just 5 for now. So question A is probably the easiest question on here. That wasn't on the quiz just now, but it's one you should expect to see every once in a while. That's just going to be 0. The integral from 0 to 0, I mean, as long as these two numbers are the same on the bounds, it's going to be 0 no matter what. But suddenly, if you bring it to be the area under the curve from 0 to 1. So let's just kind of take a look at our graph for a minute. Let's just put some kind of sampled values down. Let's say that was 1 now, right there. And we know the height of this graph is always 5, because that's kind of the example that we've chosen. So the area now of this space there would be just 1 times 5, which would be 5. Like that. And maybe it would be useful to say like units squared or something, just to emphasize that this is in fact an area under the curve. And then you could use that to hypothesize probably pretty accurately what the answer to part C is. It's going to be 10, because if we do the same thing, bring it over here, and let's say this is 2, you would just add on another square, and that would be worth 5 or whatever. So this would be 10. And so here's kind of the question. You're kind of building a function where the input variable, the variable that matters, is the one that's up there in the bound. You plug in 0 and you get out 0. You plug in 1 and you get out 5. You plug in 2 and you get out 10. So is there something we can do with the x there that would give us the area no matter what the right bound was? Multiply by 5. So a good area function for this would be a of x equals 5x.
Let's go.
That would be a good, reasonable answer for somebody to come across. The kind of the goal of teaching calc and teaching math in general for me is like, I want you to feel like you could have stumbled upon this on your own. Like, instead of your teacher showing you a bunch of rules and properties, I want you to always feel like, oh, I could have figured that out on my own. That's kind of the philosophy sometimes. Whereas I certainly learned math by being told a lot of facts by somebody, which is fine too. Now, E is going to take this question to the next level. So there's nothing special about the number 5 here. Number 5 was just chosen kind of to help ground this example in some sort of reality. So for question E, we're asked to generalize our findings for the area under the curve for any constant function. That is, could you write an a of x that was equal to the area under the curve from 0 to x of some other constant, c, where c is a constant? There's nothing special about the number 5 in this problem. It's just the number that we chose. It could be any number, and I think what you got to see is that this is 5 times 0, this is 5 times 1, this is 5 times 2, and we said 5 times x over here. If we change the number 5 to some other number, it just keeps all the answers the same. It just becomes, like, let's say it was 2, for example. It would be 2. 2 times 0, 2 times 1, 2 times 2, 2 times x. So the general area under the curve here so far, a of x, would be equal to just cx. That's it. Simple. Again, if you go back up to the drawing we kind of have to work with in this problem, there's nothing special about the number 5. It could be any constant number, whatever that is. I mean, the area of that gray rectangle right there is literally c times x, because it's a width of x and a height of c. Now, this is really easy because that's a constant function with a horizontal line. Obviously, we have all sorts of functions. We have straight lines, like this 4t plus 5 going on down below. We also have ridiculous curves, like this one over here on the board. And we need to be able to figure out the area under the curve for any of them. And that's kind of where we're going with this. So let's look at 441 for a minute. It's going to get a lot more complicated, even though we just added one little bit to this. You'll notice the only difference between 41 and 40 is that now it's a diagonal line. It's no longer a horizontal constant function. It's got a whole other thing, 4t plus 5. Now, the first thing we should do before we even try to answer anything, we should really read everything and understand what question A is asking, because that's really at the heart of what's going on today. So 441 says, what if f is not a constant function? So we got a linear equation here. Linear equations in the form of mx plus b. In this case, it's 4t plus 5. You see it graphed right there. So the first thing to do is really ponder and understand what this integral expression is asking you for, because that's what we're kind of asked for. What can that equation be used to calculate? If you look at the parts that are going on here, you'll notice that, again, 0 is locked in place. That's not changing. So the left bound of our little area under the curve thing is locked in place. What is changing is the x. That's what's moving. And that would be the right bound of our integral expression. So you kind of want to imagine, I don't really have a vertical line tool on this tablet. I wish I did. There's probably one buried in there somewhere. But imagine that the left side of this ruler is your other line. So kind of the question is that if this line is allowed to move, how does the area change, let's say, here versus here? We're really just measuring the area of that gray space from 0 to some right endpoint. We don't know what the right endpoint is. Here's another weird thing about this problem. Do you guys notice that there's another variable involved, t? 4t plus 5 instead of 4x plus 5. This is what's referred to in calculus as a dummy variable. Yeah, I know. I like that. It's just there because the variable we're concerned with is x. And the thing that's changing is x, and that is the right endpoint. We just use 4t plus 5 because we need that equation to be, a slope of 4 with a y-intercept of 5. So we use some other variable in order to lock that line in place so that we can let the thing change that we want to change, which is the right endpoint of our little integral expression. So really what we're doing, if I want to try to translate this into sentences, what can the equation be used to calculate? It's the area under f of t equals 4t plus 5. Notice how we're using a different variable for that function. From 0 to x. That's really what's going on here. Obviously, as we move that right endpoint and that right goalpost further, the area is going to increase. Our job is to figure out how that's increasing. It's not going to be constant because that line is diagonal. Every little step you take to the right is actually adding more area every time because it's getting higher and higher up. So it's not growing at a constant rate. We're actually going to use a little bit of geometry here in a minute to actually figure it out, though. So let's do that. In question B, we're actually going to put the rubber to the road and do some calculations. So we're going to use our little area thing here. We're going to figure out the area under the curve for x equals 2 and x equals 9. So let's try that really quick. We're going to use some space off to the side, or if you have like another space to write in, because this can get a little bulky. So let's really think about function notation for a minute. A of 2 equals, it would be the integral from 0 to 2 of our function 4t plus 5 dt. Remember, the input variable ends up being the right endpoint of our integral. That's where it goes. I love function notation. It is truly the language of advanced mathematics, but when we're teaching it in Algebra 1, I always feel bad because it doesn't really resonate until you get to about this point. You're like, oh. Now, to do this, we're just going to use some geometry because this is just a trapezoid. We kind of know in this trapezoid that this side right there is always going to be 5. That's always going to be the same. One thing that's going to really help this pop out is by keeping track of what's changing and what's the same. That's going to help too. I'm hoping that by doing a of 2 and a of 9, we'll be able to figure out a good a of x for later on. The right endpoint. Let's think about that for a minute. First of all, we know that this is going to be 2. That's our width. And as far as figuring out the height of that point right there, all we really got to do is figure out what f of 2 is. Which would be 4 times 2 is 8, 8 plus 5 is 13. So we're looking for the area of a trapezoid. It's important to show as much work as we can here because I really want to see what's changing, what's not. We're going to have 5 plus 13 times 2. And we can now actually evaluate that out. The 1/2 and the 2 cancel out. 5 plus 13 is going to be 18. The actual answer isn't so important. What's the most important right now is I'm going to highlight a couple numbers here because those are about to change. When we do a of 9, it's going to be basically the exact same process, except for 1/2 will stay 1/2 because it's a trapezoid formula. The 5 is going to stay the same because this left end bound is not changing. But everything else will change. The width will change and the height of the other side will change as we move this other side around. So right next to that problem, I want to do a of 9 because that's the other problem we got to do. It's going to be mostly the same, but I really want you to pay attention to what's going to change because eventually I'm going to ask you to figure out a general function for like a of n or something. So this is going to go from 0 to 9 this time. It's the same function inside, 4t plus 5 times dt. And when we go to actually figure out what that trapezoid would look like, I'll try to draw it maybe in a different pen color. Maybe it'll be over here. Doesn't really matter too much. This time, the width is now going to be 9. And as far as the height of that other side over there, that's going to be f of 9, which is 4 times 9, 36, plus 5, which is 41. So putting it all together into another calculation, again, really paying attention to what's changing and what's not, it would be 5 plus 41 times 9, like that. Again, I'm going to highlight the numbers that changed. And let's actually get the answer because it's kind of required for this problem. 1/2 times 5 plus 41 is 46 times 9. This is going to end up being 23 times 9, which is some number, I don't know.
207.
Nice, 207.
I definitely use my head for that.
Yeah, sure.
Easy.
No. That would be part B that we just did. Now again, we do that to kind of set up the pattern of what's going on, because what we're going to eventually do is we're going to, in question C, actually right now, we're going to use this to write a general equation for A of x. The area under that straight line, 4t plus 5, for any right area, any right bound. The left bound being 0, the right bound being whatever. That's what we're going to do. So to do that, we're really going to have to think about what's going on inside of this formula, because now we kind of have, this is part C, we're looking for really A of x. And that would be the integral from 0 to x of 4t plus 5 dt. So we really got to think about what we saw in these patterns. We know that it's going to be a trapezoid. We know it's going to have 1/2 in front of it. We know it's going to have 5 in there, because that's not changing. That's what's going on at 0. But the number 1341, we really got to think where that number's coming from. So let's at least write down what we know right now. We know it's going to be 1/2 times 5 plus something. So the question comes now is that where in the world did we get the numbers 13 and 41 from? Where did those numbers come from? I know this, they're over here too, 13, 41. And the answer to that is that we got them by plugging in a number into the original function. Those are just 4t plus 5 for the values t equals 2 and the values t equals 9. So if we no longer have a number that we know we're going to plug in, we at least have a formula. So in our general formula, we're just going to use 4x plus 5, because that's how we end up finding that right endpoint. So down here in our formula, we're going to have 5 plus 4x plus 5. And it might be helpful to put that in its own little set of parentheses just to help separate it out, because that's how we calculate the right bound, the height at the right bound of our little trapezoid there.
Nice.
So I'll highlight that in green too, just to be consistent, because that's where it came from. That's how we got 13, that's how we got 41, and that's how we would get any height at x. We would use 4x plus 5. The other question is, what about 2 and 9? And that's even easier. That's just whatever x was. So we're just going to put another x at the end here too. You'll notice I did change 4t plus 5 into 4x plus 5, because I actually am going to plug it in now. I mean, that's the answer. All we got to do now is kind of simplify it and make it look nice, because when we do that, I'm hoping there are some patterns that will jump out at you from the original 4x plus 5. Here, let's just go for it. So we have 1/2. Inside this parentheses, we're going to have, let's change it to 4x plus 10 times x, like that. And you know what's nice is the 1/2 can actually just cut 4 and 10 into 2 and 5. So it'll be 2x plus 5 times x. And so the general area formula is 2x squared plus 5x. There's your general area formula for this particular line of 4x plus 5. Now the real question would be, can you find a connection between 4t plus 5 and what we just did down here?
Yeah.
Do you see it?
I don't know what he's doing.
I'm not supposed to use the word antiderivative today. The CPM instructions specifically said don't start talking about antiderivatives yet, but if you were to take the derivative of that area formula, you would get right back to 4t plus 5.
Exactly.
Yeah.
So we could have just skipped all that work.
Well, you know, you prove things. That's it.
But
Yeah.
if it was right, do we
Yeah.
have to
Yeah.
prove it?
There you go. Okay, okay. Well, there's more to it than that, but so far that's a good connection to be making. Question D is going to be an even more significant challenge. Could we do this for any, like I said, kind of like the previous problem, there's nothing special about 4t plus 5. What about any value of m and any value of b? We could kind of do the same thing. Let's think about it for a minute. We know we would have a trapezoid. Well, let's think about this for a minute. If you were to plug in, well, we have a couple things we got to tackle first of all. I mean, mt plus b, this could be any line. It could be increasing, could be decreasing, any y-intercept, any slope could be represented by mt plus b. So we got to think about a couple things. I think no matter what shape you have, no matter where you are, you're going to at least be looking at some sort of trapezoid. So let's at least start with that 1/2 piece. We know that. Now, the first piece of this challenge is not going to be as easy as we think it is, because the last problem we had 5 the whole time. It was always 5 at the front of that thing. So a good question right now is, what's a reasonable guess for what the left endpoint would be in a general mt plus b? For a general any line of mt plus b, any slope, any y-intercept, what would be a reasonable thing that you could think you could probably put right in that first slot for the left endpoint if we're locking it in place?
0.
Well, that's zero. If you're thinking about 0, you're thinking about the right thing. But what you want to do is you want to plug 0 in for t. Because if you think about this trapezoid, let me try to, it's tough to draw a picture of this because we don't know what the line looks like at all. But pretty much any line you draw, no matter where you draw it on here, we're starting this adventure at 0. And at 0, if you want to know the height of that left bound, all you really got to look for is the y-intercept. And so the left endpoint is just going to be b, or the height, I guess. The height at the left bound is going to be b. If you look back at our previous example, it was always 5. Always 5, because 5 was the y-intercept in that problem.
Yeah.
If we changed the problem to be 4t plus 3, it would be 3 the whole time. If it was 4t minus 1, it'd be negative 1 the whole time. So the left endpoint is going to be b. The right endpoint, I think, is actually much easier because it's just going to be mt plus b. You got to plug that in. So plus, in its own little parentheses, mt plus b. Because that's how you would find the height at your other endpoint. Actually, let's change it to mx plus b, since that's what you would be doing here. You'd actually plug in a number for x. And then you would also have an extra x out here, because that would be the width. And that only works in this case because we are starting specifically at 0. The next section, the next question, 442, is going to say, okay, does it matter if you're starting at 0? Could you start at any number and have this still work? That's going to take a little bit longer to explore. I mean, it doesn't look super nice, but we could easily explore this and figure it out. Let's try it. What we would have is we would have equals. Let's keep that 1/2 out here in front. Let's just do some kind of cleaning up. We would have mx plus 2b inside of this parentheses. Because you can add your b's together. b plus b will give you 2b times x. And you know, you could multiply the x and the 1/2 in any order that you like. I kind of like doing the 1/2 first. So we'll have 1/2 mx plus b times x. Because the 1/2 times 2 would cancel out and leave just b. And then you would have equals 1/2 m times x squared plus b times x. And then I suppose we could ask the same question. Does that same relationship still hold between the original general mt plus b and this thing down here? In other words, again, I'm not supposed to use the word antiderivative right now, but if you took the derivative of this, would you get back to that?
I believe so.
The 2 would come down and cancel out the 1/2. You'd have mx left. Plus b, the x would derive that would be a constant, so mt plus b. You'd be right back where you were. So yes, there's a pattern that I want you to see today. We're not going to get into details about how to calculate it or talk about formulas for calculating it, but the thing that we're establishing right now at this stage in the game is that there seems to be a derivative, antiderivative relationship. And again, the philosophy here is that I want to present you with situations and problems that make you feel like you could have discovered calculus on your own. You could have figured this out if you were looking at it long enough. Isaac Newton did it in a cave with a box of scraps.
He's also a nerd.
That's from Iron Man.
Yeah, they're both nerds.
Yeah.
Man.
It is pretty incredible that those guys did that and not that long ago on the human history of timeline. Not that long ago. We're talking like 200-300 maybe years ago. With no calculators, just kind of sitting there on a rainy day.
Power of the sun.
Yeah, I know. It's pretty groovy. There was a. They found an old document from Aristotle. They had the basics of calculus figured out years in advance.